Naive Bayes is fast, but it makes a strong assumption that words are independent. Logistic regression makes no such assumption. It learns a weight for every word in your vocabulary and combines them to make a prediction. In this episode, we go line by line through how it works, how to build a sentiment classifier, and how to read what the model has actually learned. Logistic regression learns a numerical weight for every feature in the input. In NLP, each feature is a word or n-gram from the TF-IDF vector. It computes a weighted sum of all feature values. Words that are strong signals for a class get high positive or high negative weights. This sum is then passed through the sigmoid function, which converts any real number into a value between 0 and 1. We interpret that value as a probability. If it exceeds 0.5, we predict the positive class. The sigmoid function takes any real number and maps it to a value between 0 and 1. The formula is 1 divided by 1 plus e to the power of negative z. Very negative inputs produce probabilities close to 0. An input of 0 produces exactly 0.5. Very positive inputs produce probabilities close to 1. This makes it perfect for binary classification where we want to output a probability that something belongs to the positive class. We set up a sentiment classification task. Each text is a short product review, and each label marks it as positive with a 1 or negative with a 0. In a real project, you would use thousands of labeled reviews. The imports are TF-IDF vectorizer for feature extraction, logistic regression for the model, and train test split to hold out evaluation data. The training pipeline is nearly identical to Naive Bayes. We split the data, fit the TF-IDF vectorizer on training data only, transform both sets, then fit the logistic regression model. We use bigrams by setting n-gram range to 1, 2 to capture phrases like waste of and very disappointed. The predict method returns the predicted class label. The predict_proba method returns the actual probabilities for each class, which is useful when you need confidence scores rather than hard labels. One of the biggest advantages of logistic regression over Naive Bayes is interpretability. The coefficient attribute holds the learned weight for every feature. Positive weights push the model towards the positive class, and negative weights push it towards the negative class. Sorting the weights lets you see the most influential words in both directions. This lets you inspect exactly what the model has learned and catch unexpected patterns or biases in your training data. Logistic regression handles multi-class classification naturally. Here, we have 3 topic categories: business, health, and sports. Setting multi_class to multinomial tells scikit-learn to use the softmax function instead of sigmoid. Softmax extends the sigmoid idea to multiple classes, producing a probability for each class that sums to 1 across all classes. The class with the highest probability is the predicted label. The rest of the pipeline stays identical to the binary case. Naive Bayes trains faster and works better when you have very little data. Logistic regression generally achieves higher accuracy on medium to large datasets because it learns optimal weights rather than relying on frequency counts. Logistic regression also gives you interpretable weights so you can inspect what the model has learned and why. Always benchmark both against each other before moving to more complex models. You now know how logistic regression works for text classification, how to build and evaluate a sentiment classifier, how to interpret feature weights, and how to extend it to multiple classes. In the next episode, we cover support vector machines, which draw a different kind of decision boundary and often outperform logistic regression on smaller text datasets. If this helped you, subscribe so you do not miss the rest of the series.